Okay, I suppose I'll start and then people are free to join in anyway. So I welcome you all to this live session on problem solving for the subject course experimental stress analysis. Uh, uh, and my co-guide is Professor U. Sarunan from the Civil Engineering Department. I'm pursuing PhD in the Applied Mechanics Department. So the idea behind this live interaction is to solve some problems and then answer any doubts that are there. And I hope I've already told you in the previous session, but just in the interest to cover any new attendee, I'm just repeating that in case you have any other questions after this session also, you're feel free to join the forum and you can ask them there and I'll try to address them in the upcoming sessions. So we will be having weekly sessions, 6 to 8 on every Monday through this semester for answering the questions. So before we get started, if there are any questions on what we have discussed so far in the previous session, you please raise them now so that we can address it and move forward. Okay, so I take it that there are no questions. And I have also uploaded the videos. Light travels faster in ice than in calcite. Okay, okay. Mr. Rajamannar, you were concluding something with this? It's an observation you're making about light speed based on the refractive index, I suppose. Is it true or false you're asking? That you can refer to any this thing on. It is not as such difficult. I would say that refractive index is pretty standardized. So you can refer that out and you can perhaps get the answer, I suppose. Unless I'm missing something that is major about this question, in which case you please feel free to bring it up now. Yeah, okay, okay, yeah. Okay, that I would suggest you raise it in the forum because those are that part is being handled by another TAs. I meant if there is any technical questions, that is any doubt in the phenomena, that you please feel free to bring it up here. Because understandably, the access is kind of different. I do not have access to go for revaluation or to check those things. I have only been given access to previous year assignments, which I'm required to solve here. So if there is any doubt in the conceptual development, you please bring it up here. Otherwise, I would suggest that this issue you please raise it in the forum, and the TAs that are handling it will answer it. Yeah, all right. Okay, so I suppose we can get started. So let us move on to the first question for the day. The assertion is that the analytical solution is not available in the case of a problem of spanner tightening a nut. The reason behind this is that it is difficult to define the outer boundary conveniently for obtaining the solution analytically. So if there are people who want to take a shot at this, please feel free to. The idea is this question is again shown multiple times. Professor shows this a spanner, a tool which we generally come across in everyday this thing. It says that yeah, both could be true, but the question what it is trying to ask is whether the reason is correctly attributed to the assertion. So if we see that the boundary of actually all this is a free surface, if you see all this is a free surface except for one load application point. at each contact point. But in order to define this conveniently, we do not have a coordinate system because it's not a regular shape, in which case it makes us very in this case it makes it difficult to provide for the boundary conditions. As we see from theory of elasticity, for simple problems like beam and even for polar coordinate problems, for example, at allular disk, we are able to define and parameterize the surface where we want to define the loads, tractions, and displacements by means of a common parameter, for example, r theta or xyz. And in case of crack problem, we even go for elliptical coordinates. But for more complex problems, which are apparently simple when because we come across them in day-to-day life, but these surfaces cannot be captured by one unique coordinate system. So it becomes hard for us to define the boundary conditions, which is why analytical solutions do not exist as of now. So both the statements are true, and R is actually the correct explanation for A. If there are any questions here, I'll take it now. Okay. Critical zone for? No, see, actually, for the spanner, if you draw the free body diagram of the spanner alone, so we can see that it just has a shape like that, which we can cut it out. And ideally, at these 2 points, we have to define the loads. Now, depending on how deep we go into the problem, it would make a difference on the fringe patterns that you observe. If we were to simply apply point loads here, because point load is very easy to idealize in the first level courses, if we go by a point load and apply it there, we would see that from the numerical solution, we will get a singularity because the stresses will shoot up at that point alone. So what we ideally do is there is much research that has gone into it about how the distribution is, because a point load in any case, it is an abstraction. It doesn't ideally come that way. It is actually an elliptical distribution sort of thing. So the closer we go in defining those boundary conditions, example, if we were to take a segment here, and if we were to apply an elliptical distribution instead of a point load, which statically is equivalent, summing up to the same load, then we would be able to see a marked difference in the fringes. And the closer we go to idealizing this contact, the more closer our fringes are to what is observed in the experiment, thereby validating it. So these are essentially, as for the spanner is concerned, these two contact points where it connects with the nut, how we idealize the force distribution to be is what is critical for this problem, as far as the spanner is concerned. So now I don't know if I've answered your question straight away, but if you have any follow-up questions, you please ask them now. Mr. Anil, I suppose. Yeah, yeah, okay, yeah, yeah, yes. Yeah, so if we clamp it here, there will be a bending moment. Hmm. Least critical region you can see from the fringes. See, since the analytical solution doesn't exist. For example, if you take a beam, a simple beam, if you take and load, we are able to see that shear, as far as the shear variation is concerned, the top and bottom are free surfaces, so shear doesn't govern there. Whereas as we near the neutral axis, the shear becomes more. And the bending moment diagram neatly captures how the bending moment varies across the span. The idea behind this question is that analytical solution doesn't exist, so we cannot readily predict which is the critical zone and which is not. Since this question has been solved using numerical methods and has been validated using experiments, we can see from the experimental fringes, which professor also shows in the lecture, that this area would actually be dark when we see colored isochromatics. So dark meaning that sigma 1 minus sigma 2 is 0. So that is because the fringe order there is 0. So what this signifies is that the material where it is not highly stressed, there some optimization can take place. But for this, every problem needs to be analyzed threadbare and separately. So a priori, given a problem and some support condition, you can only say make some engineering guesses, but how far those are valid is contestable. So I suppose I'm not sure if I've answered you, but if you have follow-up questions, please bring them up now. Okay. Because for an unknown problem, if we simply ask that which are the critical zones and which are not, it is like a first level approximation we'll make. Ideally, what we see here as a first level approximation is it is nothing but a beam where you can say that it is undergoing some sort of bending, because this portion is just undergoing bending. Then more and more close we go about the arms of the spanner. As we improve our idealization, more information we are able to get out of it. And this reaches a tipping point where we are no longer able to capture this analytically, which is where we resort to numerical and experimental techniques. So to a priori just gauge where will be the stress concentration is a matter of experience, which can only come by if you have some experience in numerical modeling and experiments. Okay, there was some question in the chat box about critical zone in the sense of stresses. Yeah, so in the sense of stresses, yes, the patterns which is shown in the lecture, you can refer to them and try to make some intelligent guesses based on what will be discussed next week. Because next week we will be discussing the basis foundations of photoelasticity. So what each and every color means would be discussed. Based on that, I would suggest that you reflect back on the fringes that were shown, the stress patterns that were shown in the lecture for the spanner, and try to identify which will be less stressed and which will be more stressed. And if you have access to numerical softwares, packages like Abacus, I would suggest you also try to model it and see how close you can come to what was shown. You would see that there are some other tweaking required in order to get an exact match, which is what has been done in that research paper that professor showed. Okay, so I suppose this question is clear, so I'll move on to the next problem. Coherent gradient sensor is essentially a variation of caustics, a variant of photoelasticity, a variant of shear interferometry, a variant of halography. Actually, this is a variation of shearing interferometry only. And as professor also mentions in the lecture that these coinages, each and every incremental development that happens over a method, they coin a new term in order to make it more attractive and for salability purposes. But this ideally is a variation of shearing interferometry for analyzing slopes and curvatures. And coherent because we have a coherent light source. Coherent light source means that all the light beams that are emitted are in phase. There is no out of phase this thing. For example, a laser where everything is in phase. So you have control over the input light, and whatever difference is brought about in that, in the recording, in the light that you record after incidence on the model, the naturally the model is responsible for that. From that inference, you can gauge something about what is the stress or what is the displacement that has taken place, keeping in mind our understanding of mechanics. So I hope that is clear. So if you move to the next problem, the higher density of fringes in a particular zone of a fringe contour obtained from an experimental technique indicates which of the following: the value of the variable it represents is constant in that zone, it is low in that zone, it is high in that zone, or the density has no significance to play. Higher. Yeah, so this has much to do with what we discussed as what exactly a contour represents. So we had discussed it using a parameter in the last session, which is a function of space, let us say, and a function of time. That parameter could be scalar, a vector field, or a tensor field, or anything. So ideally, when we try to plot this, this is a surface in three-dimensional space, and if it is time varying, that surface is changing with time. If we were to keep time constant, it is just a constant surface. Its projection on a plane for easy visualization is what is called as contour. So each point on a contour represents the same value of that parameter. Now if we were to have this as a contour and then the other one as a contour, so ideally these two are, this is p equal to k1, this is a contour for p equal to k2, because a contour by definition it connects the points which are having the same parameter value. Now this question is asking if we have closely spaced contours, then what does it indicate? Because of our by definition a contour can only join points which are of the same parameter value, and if it is closely spaced it indicates that the variation in that parameter is quite high. So if we were to draw uh, if we were to see the surface which we were talking about, which we projected onto the plane, it would be climbing. So that is why the variation is high in that zone. So whenever we see from optical techniques, whenever we load a specimen and see, and we are able to see that the fringes, whatever they represent, whatever the contours they represent, if they are very closely spaced, it indicates that the stress concentration is, that the stress gradient is very high. So if there are any questions on what we discussed, you please feel free to ask now. Okay, I take it that it is clear. So let us move on to the next question. If the location of a point where the measurement of stresses has to be carried out, yeah, yes, sorry, yeah, yeah, you have any question here? Okay, anyway, this PDF also I'll be sharing. I hope you have accessed Swayam portal where they have uploaded the video, and the PDF where I'm writing this is also available there for week one. So these also I'll be sharing. So I would suggest that you, I mean, you can write if you want, but ideally this will be supplied to you anyway. So you can see what suits your convenience. Moving on to the next question, if the location of a point where the measurement of stresses has to be carried out is known a priori, the preferred experimental technique for precise measurement is brittle coating, strain gauge, photoelasticity, or holography. So you guys can take a shot at it, then we will discuss this. By the way, it was uploaded like on a weekend, right? I had uploaded it last Monday. We had the session. I uploaded the session on Monday itself. By Monday, end of day, I had uploaded it. So the Swayam people must have taken that time to reflect on it and make it publicly available. So wherever you see the live session, it will take you to, essentially it will take you to a Google Sheet where the YouTube link would be given and the PDF link would be given. Starting this week, the same sheet would be used because it has week 1 to 12. So whenever I upload, I'll be putting it there so you can access it from there. So I hope that clarifies it, Mr. Rafael. Okay. Yeah. Okay. So, okay, I'll just repeat what I had mentioned. So the idea is that for characterizing the stress field, we require at least three independent stress components that are there. So why we go for brittle coating is that if by that very name If we see that we have applied brittle coating on a material surface and then it is stressed, brittle by its nature, it will crack in the direction that is perpendicular to the maximum principal stress direction. So once we have a crack pattern, we can analyze each and every point where the crack path crosses, and we are able to identify which is the principal stress direction at once. So if we were to know the principal stress directions a priori, then we can ideally place only two strain gauges and make the characterization instead of three strain gauges. So at every point of interest, we are saving one strain gauge. So when you multiply it by thousands, where we are analyzing big structures, so this will be of much benefit. Now the question says that measurement of stresses has to be known, has to be carried out, and it is known a priori, which implies that brittle coating has already been applied on the test specimen, and we already know that what is the direction in which principal stresses are. Then which is the preferred experimental technique? Because photoelasticity and holography are whole field techniques. They give the whole field information. But ideally, if I want to make very precise measurements at a point, then I have to go for a point by point technique, which happens to be strain gauges. So the correct answer to this is strain gauges. So if there are any questions, please ask. Then this is followed by strain gauges. Cannot be applied when dimensions are small. But last time we discussed that strain gauges cannot be applied when dimensions are small. Okay, but where is that constraint put in this question? Yeah, so I hope that is clear. Actually, see, at the time the course was being taught, there was one kind of technology available. Now, if you see that even professor has very comprehensively covered what could be the future by gauging what are the methods that were prevalent and what are the methods that were coming up, we can kind of extrapolate what all could happen in the future. So the idea is that now with sophisticated technology available, manufacturing technologies available, we are able to go for smaller strain gauges also. The idea is what will be suitable for a particular application is a subjective call. Now the idea behind this course is not to enforce that only this can be done and that cannot be done. It is to have an overview of what is the physics behind each and every technique and what are its limitations and what is the range of its application. So based on that, one any researcher or experimentalist is the idea is that they should be able to take a comfortable call on which are the methods that could be applied there. So that is what this training is towards. So I hope that point is not missed. Okay, so it is a follow-up of what we just discussed. The minimum number of strain gauges required to obtain all the strain components at a particular point in a material for a given case, principal stress directions are not known. So when principal stress directions are not known, ideally we require three independent components. And in the orthonormal basis, we would require at least three in order to characterize them, because in a plane stress tensor, we have three independent components, two being the normal stress and one being the shear, which is why we require three. So if there are any questions, I'm happy to take them now. Okay, so I take it that it is clear. All right. Okay, the information of stresses interior to a body can be obtained efficiently by which of the following experimental techniques? Is it strain gauge? Is it Moire interferometry? Is it digital image correlation? Or is it photoelasticity? So naturally, when we say that we have a body, let us say that we have a body like that. Let this be a three-dimensional body. So now if we have to see the stresses interior to it, naturally there should be some kind of mechanism that transmits. So ideally this is suitable for optical methods where light can pass through it if it is a transparent medium and we are able to see what is happening at each and every point. So naturally photoelasticity being a whole field optical technique, it can help us identify stresses at each and every point. But there are different variants of photoelasticity that would be required to do this. When we go for normal transmission photoelasticity where we load it, we only analyze a plane. But since plane cannot take compression, we would have some thickness, assume it to be in plane stress and conduct the experiment. Whereas if we were to have a very long uniform prismatic section, which where load and displacements are not a function of the third dimension, then we would essentially cut a slice, take it to be in plane strain and analyze it. That is idealizing and bringing the problem down by one dimension to two dimensions. Now, if we were to really analyze a complex problem where there are three dimensions, then there is a technique called stress freezing. By loading the model and subjecting it to particular thermal cycling process, we will be able to freeze the stresses in there and then appropriately cut slices where we want normal incidence to take place and place it in a polariscope. So that is one way to study stresses interior to a model. No other method, first of all, measures stresses. It only measures strains and we back calculate stresses. Photoelasticity is the method which directly measures stresses in the sense that it is directly related to the light intensity instead of going through the strain route. So the answer to this is photoelasticity. Digital image correlation, we know that if we have a specimen and then we apply speckles on that, essentially apply speckles on that and take photographs, and the each of the photographs is correlated in order to find out where each point has moved. That is the very fundamental principle behind digital image correlation, which ideally measures surface displacement. So it is a surface phenomena, it is not an interior study. Moire interferometry is also, if we see, we place the grating in one way and we get the displacement. When we view it from the perpendicular grating, we will get the displacement in that direction. So Moire interferometry also is ideally a surface measuring phenomena, surface displacement measuring phenomena. And strain gauges, we are only pasting that on a surface. The assumption is that when we place a strain gauge on the surface, the surface strains are faithfully carried by that strain gauge, which is calibrated and amplified using an instrument in order for us to make meaningful readings. So all the first three options, if we see, they are measuring only surface displacements or strains. So in order to arrive at stresses interior of a body, we can only go for photoelasticity. I hope that is clear. If there are any questions, please feel free to ask now. Yeah, yeah, yes. So actually, it goes by subsets. So the entire your region of interest would be divided into subsets of pixels, and for each subset, you will be setting a number based on which the subset size was vary. That these many pixels are the ones you are following, and each and every image, as progressively it is taken, it will be correlated with the previous image in order to track each and every particular, and then there is some averaging that is taking place in the algorithms. So these are all sold by commercial softwares which does this, but there are certain open source algorithms also which you can refer. in order to see how that tracing takes place. It is essentially you are taking an image now, and then at t plus 2, t plus t naught plus t, you are taking another image and you are trying to correlate this. So there is algorithm to essentially identify in each subset each and every pixel and where it moves to. And then in order to make it statistically stable, there is some time averaging that is taking place to the extent that it doesn't affect the result in any major way. So there are some approximations that are there, but this is the basic principle on which it works. Uh, yes, up till the end of the, not failure, up till the end of your experiment. If you want to go till failure, you can go. So we will be capturing the entire specimen region of interest that we want. For example, if we were to characterize a material, let us say, and then we apply speckles all over it except this thing, and then we capture images of this entire specimen based on some frame rate. And once you load it, slowly what would happen is that this would, if we were to load it till failure, this would have moved, and there is some necking that would take place, like that, something like that. So these speckles would be traced by your algorithm, and it would try to, because the speed at which, the frame rate at which the sampling is done is quite high. So we are able to say at each and every frame where the point would have moved. So we are essentially getting a time varying displacement field which is being captured. Once we get that, we can differentiate that with respect to the spatial variable and get strains, from where we can use the constitutive relations to get the stresses. So yeah, oh yeah. Now this will just be using one camera. Now if we are using two cameras at an oblique angle, there are ways and means to measure the out of plane displacement also, not just U and V, but W also we can measure. But it requires a minimum of at least two cameras for two image acquisition systems, which will be again intertwined and correlated. Okay, the experimental techniques which can be employed for determining the stresses induced in slamming of automobile doors is Moire interferometry, caustics, holography, thermoelastic stress analysis. Actually, this could be a little dicey, but this question has been framed based on what is discussed in the lecture. Yeah, so thermoelastic stress analysis, wherever there is load, we are able, what we notice is that there is a slight change in temperature of that specimen. So if we have sufficiently uh, sensitive sensors, then we are able to correlate what is that thermal change to the load that was applied. So that is the basic principle behind thermoelastic stress analysis, which is what is used. So it is kind of a direct question, but the idea is to understand what each and every method tries to measure, what is the physics and what is the application and the range of that application. So if we move to the next question, the experimental technique which can be used for recording the mode shapes of a vibrating component is, yeah, the the idea behind thermoelastic stress analysis is that whatever temperature change is caused due to repeated loading or cyclical loading is translated to a change in temperature which is measured by sensors and calibrated against a known problem, so that we can extrapolate that same for an unknown problem in order to analyze how the stress patterns are based on what is the variation we get in the temperature. This is what is applied for problems like slamming of automobile door. This is just a crude example taken from the lecture, but the idea behind this is to understand what is the physics behind each and every method. And slamming, When we close and open automobile doors, which sorry? Yes, 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 yeah, okay. So the experimental technique which can be used for recording the mode shape of a vibrating component. This is again straight taken from the lecture. But mode shapes for vibrating, you need the displacement vector. At each and every time instance, you need the displacement vector with which you can track what is the velocity and acceleration. And based on that, yeah, yeah, using accelerometers you can find. Yes, but since that is not given, what other experimental techniques at your disposal, whatever is given, how could you find that out? And accelerometer also has one problem that if you were to place, you will have to go for some assumption on lumped mass. How many accelerometers can you place? You must pose some cap on the degrees of freedom that you are trying to analyze. Whereas holography gives you a displacement vector which is whole field in a sense. So you are not making any approximation towards the degrees of freedom for that system. Is it clear, sir? Yeah. Okay. Yeah. So what we require is here is the displacement vector in order to characterize the mode shapes, which is given by holography. And this is also discussed in the lecture. And why holography? This has another point to be kept in mind is that holography is very, very sensitive to vibration. So if you were to do the experiment, because it has one object beam and the other one is a reference beam. So because these two are distinct, if there is any vibration introduced, unequal vibration that is introduced onto one of the beams, this will reflect in your results and it could throw off your analysis. So stringent vibrational control is very much required for conducting holography, whereas that is not the case in photoelasticity because we have the same reference beam which is split into two because of a phenomena called stress induced birefringence. Since it is of the same phenomena, whatever vibration is introduced to one is directly translated to the other also. That is why photoelasticity is not very stringent about vibration control. So this is something to be kept in mind. Okay. Answer true or false for the following questions. Yeah, it is to be reported in one particular way. And again, because someone had brought up the issue of having answered in a particular way and not getting the credit for that. So you please take note of how it is to be reported. Because this is computer corrected, there naturally has to be some restriction on how the student should report in order to avoid any mix up. So in case it is not clear, please ensure that you get it clarified in the forum by asking the TAs much before the assignment closes. So that would be that would avoid any confusion and also help out others if they are having the same question. Okay. So point A is a strain gauge measures strain tensor at a point at a particular point. Speckle methods in its variation of shearography is very used for NDT in aerospace industries. Brittle coating got its name because it is used to measure stresses in brittle materials. Strain gauge is an ideal technique for in situ measurements over long periods of time. So if we were to go for the first option, strain gauge measures strain tensor at a point. We know that at a point in a plane condition, strain tensor has three components. Yes, so it only measures strain along the gauge length. If we were to place a strain gauge like that, then it would be measuring strain only along its axial direction. Same goes for any other generic direction. So it only measures, now it is up to us how we place this in order to measure normal strains. If we know the principal stress directions, we can align the strain gauges with those direction and just arrive at two quantities where there is no shear strain. And if we don't know, we would have to go for strain rosette, which is a combination of three strain gauges in particular angles. So the strain gauge as such does not measure the strain tensor at a particular point. It only measures a component of strain. That is a particular entry of a strain tensor rather than the entire strain tensor. Speckle methods in its variation of shearography is very useful for non-NDT, non-destructive testing tool in aerospace industries. This we had also discussed in the last session where speckle methods are used for finding out whether there is any delamination in in space applications. So it is definitely used there, which gives you out of slope of the out of plane displacement. So if you see a uniform pattern and at one point you see that there is some distortion, that indicates that the out of plane displacement slope is distorted at that point, in which case it indicates to a delamination. See, brittle coating got its name because it is used to measure stresses in brittle materials. Naturally, this is false because we discussed what brittle coatings are. We apply a coating and then by its virtue of being brittle, it cracks in a direction which gives you principal stress directions at once. Once we identify that, it will reduce this along with strain gauges are used to characterize point by point phenomena where you can significantly reduce your instrumentation requirement. Strain gauge is an ideal technique for in situ measurements over long periods of time. Yes, once strain gauge pasting is very sensitive, there are certifications that are given out every year, and it is not everyone's cup of tea to paste strain gauges. It's a very sensitive equipment. It's a very sensitive method. So once we place a strain gauge, there are ways and means to check the installation. Only if it is properly pasted, then we can be reliant. Then its results can be relied upon. Otherwise, as professor also said that you are measuring anything under the sky. So it is very important that it is done properly. But once it is done properly, and if it is properly protected, then it can serve over long periods of time. One classic example for that is in our own lab, we have a thin and thick strain measuring machine where strain gauges are pasted, and those were pasted about a decade or so back, and they are still holding. Although one has debonded, but most of them are still holding, so it can definitely be used over long periods of time. So this is definitely true, provided it is pasted properly. And yeah, okay, okay, moving on. Yes, yeah, yes, okay, yeah, yes, yeah. In space applications, mostly okay. Nowadays we are going for composites. That's fine. Okay, which has a varying in let us say heterogeneous. Yeah. So what is your question in here? Okay, okay. Okay. No, see, characterization is one thing. To characterize a material means to identify all the components of the elasticity tensor, so to speak, or to know how strains and stresses are related. That is the basic idea here. Now, for composites, yes, it is heterogeneous, so there will be no everything will be coupled. So we cannot go for decoupling, and we cannot say that only, for example, we say that for an isotropic material, we require only two elastic constants. Others are all dependent. Only these two independent components are required. When we go for orthotropy, when we go for anisotropy, it increases. So there are more number of parameters which you have to evaluate. This whole process comes under the uh, purview of characterization of the composite. Whereas what we are talking about in this problem, in this specific example, is how we can do non-destructive testing tool, how we can use that in order to check the quality assurance. That is, if delamination is taking place, then how out of plane displacements slopes would change. So if there is anything that has debonded, because it is in such a expensive equipment, it needs to be threadbare analyzed. So for that, we are using this shearography, which is quite sensitive, and it can measure the slopes of the out of plane displacements. That is what we are talking about here. Whereas if we go to composites characterization, it is an entirely different purview of research. And there also, actually, DIC is thoroughly being applied. It is not that it is not being applied, just that you require more components in the elasticity tensor than just two. So you should be devising your experiments in such a way that you are able to measure the response of one over the other. For example, there could be more than one Poisson's ratio in those problems. If you apply a load this way, the response will be different, and if you apply the load in the opposite direction, the response here could be different. So you essentially go for mu1 and mu2 instead of just a common mu. These are problems of characterization, and what methods you apply for characterization. DIC is also applied for characterization. It is not that it cannot be applied. Heterogeneity would reflect in your results, ideally speaking. So it is not that when we are applying DIC, we only want it to be linearly elastic. The idea behind applying DIC for characterization is to find out whether it is linear response or not. So I don't know if I've answered your question, but if you have any follow-up questions, you please bring them up. Yeah, yeah. No, that is art. Yes, yes, that is one variant of speckle method, which is digital image correlation, which has some algorithm and number crunching taking place. Whereas for if we go for shearography and very what you call very sensitive surfaces, there your accuracy can improve manifold. One variation of speckle is that we artificially introduce speckles in form of white and black patterns, which we read using many images and correlate. That is the method of digital image correlation. Yeah, please go ahead with your question now. Okay, 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 okay. Okay, you can think of it this way. Yeah, as you said that there could be matrix delamination or fiber delamination. But essentially, the idea in quality control is to avoid any kind of delamination for the product to go ahead. Now, what has caused this is again a purview of research, and which method to apply in order to study that is a subjective call. Whereas, if you see at the in the assembly line, if you were to check if there is delamination or not, regardless of the cause, whether it is matrix delamination or a fiber delamination, if there is delamination, how will you measure it? By seeing the surface. That is what this shearography gives you. Okay, speckle pattern would be more erroneous because of. It would not be more erroneous. It would just indicate whether delamination has taken place or not. I agree that it will not tell you the root cause of the delamination because of a matrix failure or a fiber failure. But essentially, to understand whether delamination have taken place or not, whether to demarcate this product to be okay or not, this can be used. I hope that clears it. Okay, so let us look at this question. At point A, as shown in the given figure, stress vector is 0 and stress tensor is not 0 and all the other four combinations. So if you want to take a shot at it, please go ahead. Then I'll try to explain. Stress vector is 0, stress tensor is not 0. Okay. Yeah, so because if we see that corner, the normal to this surface goes in this direction, let us say n1. The normal to this goes in this direction, let us say n2. At that particular point, we know from Cauchy's formula that traction or the stress tensor is nothing but your stress tensor acted by some normal vector. So because of that ambiguity, what we would see is even if the stress tensor is non-zero, we would be getting, that is, okay, let me explain this way. If I were to take a point here, let us say this is sufficiently away from the loading point. In such a case, if I were to draw if I were to populate the stress tensor here, I would see that it will be 0, 0, 0, P by A if the cross section is A. Now, if I see at this point, my N is nothing but 1, 0. So, if I see the traction at that point, on that surface, what it will come out to be is 0, 0, 0, P by A and 1, 0. So, my traction comes out to be 0. So, the stress vector is 0 there, but the stress tensor is non-zero there. Whereas it is not the same uh, thing taking place at that point. At a corner, because there is ambiguity, the only way to resolve this is the stress tensor also has to go to 0. So ideally both stress tensor acts as well as stress vector is 0 at that point. So if you have any questions, follow-up questions, you please ask and I'll answer based on that. Yes, so a free surface, what it, let me explain this. A free surface, you can think of it as a short for traction free surface. Traction is nothing but your stress vector. So if we see that this surface is free. This surface is actually free. What that implies is traction vector is 0 there. We just saw that traction vector is 0. But the stress tensor at that point could still contain some non-zero components. Because traction at a point is not only dependent on the stress tensor there, but also on the normal to the plane which you are studying, which you are examining. That is why it is quite possible that one of the components of the stress tensor might not show up in your traction vector because it is surface rather than the entire stress tensor at that point. In this corner, normal load is not defined. In which corner normal load is not defined? Corner A, you are saying? Okay. Normal is not defined. Yes. So if normal is not defined, mathematically speaking, in order for the stress tensor to go to 0, stress vector to go to 0, stress tensor also needs to be 0. This can also be threadbare analyzed by first principles if you see that shear cannot cross a free boundary. And so ideally this is a free surface. So for both to be 0, your stress tensor necessarily has to go to 0. I hope that it is clear that a free surface indicates that it is a traction free surface. It does not indicate anything about the stress tensor, which has to be analyzed separately based on the case in point. If we see one of the examples which I showed, that we are having a normal that is in some other direction, that is outward towards x, and the load is applied in a perpendicular direction. If we see that stress tensor does have non-zero components which does not get captured in the stress vector, so stress vector can definitely be zero on a free surface. That is what is the definition of a free surface. But stress tensor need not be zero. It is only zero in very specific cases. For example, very sharp corners, their stress tensor is zero. So if stress tensor is zero there, what we will see when we load it in photoelasticity, we will be able to see the stress pattern. What we will notice here is it will be black. Black indicates that the fringe order is zero. Clear, thank you. But if we shear stress cannot cross a free boundary. Okay. Let us say that we have a section like this, and this is my material. Inside this is my material. Now I take a point here. I have not applied any load there. So it is a free surface. Now if I were to draw my stress element there, let us say that this is a free, this top one, this top is free surface. I know that by definition now. Now let us say that my shear crossed that free boundary. This shear, it crossed it, as we can see here. If this were true, then naturally by our complementary equality of complementary shears, these components also have to exist. These components, which I have shown in a different color, in pink color, would also have to exist. And this, if it did exist, then this is no longer a free surface, which is why it violates our initial assumption, which is why shear cannot cross a free boundary. Is it clear, Mr. Raphael? Okay, I hope that it is clear. It is because we started with the assumption that shear does cause a free boundary. We took a, yeah, crossing meaning if you have a surface like this and something crosses that. So that is what is implied here. We have a free surface like this. We have a free surface like this, and then at some point my shear crosses that. Is trying to cross that, right? Here it is trying to cross that free boundary. Once it crosses, by the equality of complementary shears, top also should have existed, which violates our initial assumption that it is a free surface. This is what it means. Okay, I hope that is clear. Yeah. Okay. So let us look at this. Is there any question? Yeah, right. The advantages of numerical methods for analyzing a problem compared to other methods are the shape and geometry involved in the problem does not pose any restriction. It is possible to get whole field information. The computational effort is less. It is easy to obtain 6 stress and 6 strain components and 3 displacement components. It is easy to conduct a parametric study. So if anyone wants to take a shot at this, please go ahead. All except computational. Yeah. So as we saw that we did start out with a problem of a spanner which can be conveniently captured by numerical techniques. Then it is possible to obtain whole field information at every point. Based on your discretization, we can get the uh, whole field data, the stress, strain, and displacements. So it is easy for us to obtain stress, strains, and displacements at every point. Once the displacements are solved, then stresses and strains are automatically calculated. Yes, after calculation we have, yes, initially because it is displacement based, so we will be initially getting the displacements based on which strains would be calculated by interpolation, and by differentiation, and subsequently stresses will be calculated based on the material model that you have defined. And it is easy to conduct a parametric study. Computational effort is naturally not less, it is much more. Depending on the problem in hand, it might require you to go for some high performance computers in order to solve that problem. So computational effort is not less, it is much more. It is easy to conduct a parametric study. What is meant by a parametric study? Essentially, any mechanical problem would involve some play of parameters. Now, in order to understand the role of each and every parameter, in by the assumption that they are not coupled, the general practice is that you will hold one constant and move the other, and vary the other, and study the phenomena and do the other way around. And then based on the data that you have gathered, you will try to draw some inference. That is what is a parametric study. So once we have a model that we are sufficiently confident captures the physics of the problem in hand, by maybe validating it using an experiment, we can vary the parameters easily in the computer model and try to analyze it, what the effects are. So that is what is called a parametric study. And numerical methods are very helpful in conducting parametric study and optimization. So if there are any questions, by the way, there was, there were a question in FEA course. In FEA, it is always true the information on the boundaries are exact. Is it true for Neumann condition also? Interesting question. But okay, if you take a beam and we idealize this to be fixed. Okay, we idealize this to be fixed. So in FE, you will go and define your boundary conditions as u being 0, displacement vector being 0. This you have applied the boundary condition, you have got your results also. But if you were to see this in reality, let us say that it connects to a portal. Let us say that it was like that. There was some column which you idealized that it arrests all the rotation, and you have modeled only this portion, only this beam which is of your interest. You have modeled it using a arrested end, where displacements you have arrested and you have provided the boundary conditions appropriately. But is this actually reflecting the reality? In essence, these columns also have some stiffness. These are not perfectly rigid, so these would also rotate. Essentially, this would also cause another rotation in the beam. So it is a question of how close you are trying to match it with reality. There is an argument, yes, this might not, if the stiffness of these two are much different, then we need not worry much about this rotation. But there are some inherent assumptions that we already make in our idealization and which we translate to FE using our boundary conditions. So it will only consider the boundary condition that you have given. If you were to say that displacement is totally restricted, or if you were to allow for some partial restraint and allow for some displacement, both would give different result. It depends on how sensitive an analysis you are doing. So I'm not sure if this answers your question, but because finite element is essentially idealizing the problem how we are posing it. So in order to get meaningful results, we also need to provide some meaningful idealizations. Okay, I take it that it is clear. Let us, yeah, let's go further. So the next question says the given figure represents the isochromatic fringes. Isochromatic we discussed in the last session. It is nothing but the contours of constant principal stress difference. So the given figure represents the isochromatic fringes observed in the case of a disk under diametral compression. At the regions marked inside these red circles, the value of the principal stress difference is high. it is low, the gradient of the principal stress difference is high or it is low, the stress concentration is high or it is low. So essentially we are speaking about principal stress difference, the gradient of that and the stress concentration. Any answers? Yeah, I'm sorry. The given figure, it is showing the isochromatic fringes as we observe in experiments. For a case of a disk, we have a disk which is applied with a compression, equal compression along the diameter, vertical diameter. So the value of the principal stress difference is high low, gradient is high low, stress concentration is high low. Naturally, as we discussed that as the fringes onto, so gradient is very high, yes. So the gradient of the principal stress is very high. And if we see actually it is climbing. If we see this is a free surface. Except for these 2 points, except for these 2 points, the entire boundary is free. So essentially, our fringe gradient increases in this direction. Is from low, it increases to high, like that. So as our fringe gradient is increasing, our fringe order also increases. So the difference of principal stresses is also increasing. So the value of principal stress is also increasing, and it is near the load application point. Definitely, it is a stress concentration. So if you were to model it using numerical techniques, and if you just take a circle and in FE you apply the load at one particular node, you would see that it will distort enormously. So it will not give you what you observe in reality. In order to do that, you will have to assume some distributed load instead of a point load. So that is where the abstraction of point load fails, and we require theory of elasticity to explain how contact loads are applied. How did you deduce that the values are high? Value of the principal stress. Yeah, because it's a free surface. And as we move towards the load application point, your principal stress, your fringe order changes. Essentially, we will be numbering it like this. This will be 0, 1, 2, 3, 4. Like this, each and every fringe band will have a particular number. Because I said that sigma 1 plus sigma 2 is just some constant. That constant will, what it is, we will see next week. But that constant, so it will be from, yeah, okay. So that constant will vary as you go up the fringe gradient. That is why principal stress difference is high, gradient is high, and it is a stress concentration. So I hope this is clear. Yeah. Okay. No, if you were to, okay, if you take a plane and then you apply a uniformly distributed load. Now, if you take the same plane and you apply this, let us say this is W, kilonewton per meter, and this is L. Now you apply a load which is WL in quantity over the same L. Do you think that the response would be same? Yeah, because there is no geometrical discontinuity here, but still the response will not be same. Your stresses will get concentrated about this point. Now, if I were to zoom into this point, this is also an abstraction that WL is applied at a point. Because the material deforms, there will be some contact length over which it is applied. But that contact length will be minuscule as compared to L. That is why in our first level analysis we take it to be WL, applied as a point load. But if we go closer and closer to how it is actually getting applied in reality, we will have to bring in some deformation picture. But nonetheless, even these two are statically equivalent, we can see that the response will be much different. And this doesn't have any geometrical discontinuity. So geometrical discontinuity bringing in stress concentration is only one reason. There could be load, there could be other things that could be bringing in stress concentration because of that. For example, as you said, as you correctly pointed out, if we have a, let us say, if we have a plate and then we are applying it with some load, as soon as we bring in a small hole there, the entire picture changes. There is a geometrical discontinuity which definitely affects your stress concentration. Whereas if I have the same plate and I apply at a point, I put a hole and then I pull that hole instead of having a grip and pulling it together, that also creates stress concentration. So there could be more than one ways to create stress concentration. Loading also plays a part in that. Yeah. Okay. By strength of material, it is not the same. Yeah. So even by the first level course, if it is not the same, naturally, when we go to a second level course like theory of elasticity, the difference would be much more pronounced because even in strength of material, we have made many assumptions. Neither of these two cases are actually true in case of strength of material because both have shear varying, and strength of material only studies beam with a constant shear, zero shear span. Okay. Material developments have always influenced the advancements of methodologies for experimental evaluation. Match the following materials with the corresponding experimental techniques it has influenced. I tried to look up this Kangal, which is discussed in the lecture, but I couldn't find much material about this. So I would definitely get back to you on this in the next class. So I've taken note of this because I just don't want to say something that I've not fully that I've not studied up. So I didn't see that. Okay. So this material, what this has, how this has influenced, this I'll take a note and explain it, try to explain it in the next session. But as of now, let us, with the knowledge that we have, let us try to address this. Photoresist. What is photoresist is essentially a material that is light sensitive. What it means is if we were to expose it to different kinds of lights, it has the ability to change its properties. So what we do is it has helped a lot in holography as well as making very fine gratings in Moiré interferometry, where we have a base material over which we will be applying a photoresist and apply and expose it to a particular light pattern, which will essentially change its properties along those exposure areas. So this is widely used in holograms and also in Moiré interferometry. So photoresist has led to development in holograms. Contourable plastics. Contourable meaning any shape it can take. For example, if I have a complicated shape and if I have to do stress analysis on this, it is quite hard. So what we will do is it is more like a coating. So essentially we have plastics which we can just set it over this and allow it to cure. And once it cures, we can apply something called variation of photoelasticity called reflection photoelasticity, where we will impinge the light like this and study the response in the same plane instead of going on the opposite direction. So contourable plastics are also called photoelastic coatings, which have helped a lot in aerospace applications also. And even in the airline industry, this has wide applicability. So contourable plastics is used in a variant of photoelasticity called reflection photoelasticity. And this is a material which has made which is used in sensors for the cameras. If we see, we have uh, a sensor which can record information. So this material has been used in sensor which is temperature sensitive. So essentially speaking, we have a camera which can detect variation in temperature, which has been made possible by this. And where do we see where do we try to study the change in the temperature because of the applied stress? Is thermoelastic stress analysis. So essentially, this is B. And this, even it is mentioned in the lecture that this helped with the development of high temperature resistant strain gauges. But as I said that I have to study up more about this material, so I'll definitely get back to you regarding this in the next session. So if we were to see C, D, B, we can see that our option B matches. So if there are any other questions on this, please feel free to ask. I'll possibly try to figure out more information about this and also provide a okay and also provide some reference for this when I post this PDF, or I'll cover it in the next class. Okay. Actually, these are taken straight from the lecture. So if you would have seen the lecture, I suppose you would have definitely got what it's because these are straight away taken from the lecture only. So I would suggest that when you take the lecture, you try to take down notes when you see the lecture so that you don't miss out on the information that is being said. Because for starting next week, we'll be moving on to basics of photoelasticity and how it has come. Today, I understand I forgot it all. Yeah, so it is better that you take the notes alongside watching the lectures. Okay, so I hope that is clear. Okay, strain gauges can be employed in which of the following cases? To make in situ measurements over long periods of time, as we had seen one of the previous questions also. Definitely, once it is pasted well and protected, it can pass on data for long periods of time. To measure internal stresses, we saw that this requires a variation of photoelasticity called transmission photoelasticity and a technique called stress freezing in order to obtain what is the stress pattern inside the material. For obtaining information on remote locations, yes, definitely, because internal stress is not there. Yes. So for remote locations, it is not possible for us to do optical methods because it is not accessible. So if we were to paste strain gauges there, and we can even monitor it sitting in some other state, that is also quite possible. And in measuring rotating components, yes, this is also possible. And this has been discussed in the lecture also. So in order to measure, because strain gauge at one particular point, if it is pasted properly, it can even record up to 1 microstrain. This can be the accuracy of strain gauge if everything is done by the book and it is properly employed. So it is extremely high precision provided all the protocols are followed. So in rotating components also, we generally we can paste strain gauges and maybe use slip rings, and we can get the wires connected to your data acquisition system. Or now we can also go wireless. So that is also quite possible. So except for B, in all other applications, strain gauge can be conveniently applied. Remote location meaning, okay, actually uh, there is a study going on about Pamban Ridge, which has recently been decommissioned, I suppose. But how the strain variations are and whether to what traffic restrictions to pose, that project was given to. Yes, bridges constructed in forest areas and transmission towers. You can go to hill stations. There also they'll be placing some wires, transmission towers, and all that. So, in order for us to make measurements from remote locations, it is ideally suited. As I was saying, Palm Bridge is one example, with the project for which was handled by our civil engineering department at IIT Madras by Professor U. Saravanan. So there were strain gauges pasted, carefully pasted with all the protocols followed in Palm Bridge, and we were able to see real-time data acquisition here. So sitting here, we are able to monitor that. So it is quite possible. Okay, this is another variant of what we saw. Which of the following statements is true related to a free surface? Yeah, yes, yeah. Far field stresses and remote stresses. Can you tell me in which context did you come across this usage? Remote stresses. Okay, okay, okay. Yeah, yes. Okay, yeah, then there is essentially, I don't think in this connotation there is any difference. Far field stresses and remote stresses are one and the same in this context as far as I can understand. Because how you would analyze this is that you will take another, how this is analyzed in theory of elasticity is that you will take another big disk whose radius you will equate to zero and apply a radial boundary condition there, and using stress transformation you will be getting sigma r and sigma theta. So that is how this is done. This is considered to be at r equal to infinity, this boundary. So I'm not drawing it to scale. The hole is very small as compared to the entire plate. So this problem is solved in theory of elasticity by assuming a another boundary at infinity. So remote and far field essentially connote to the same thing, as far as I can tell. Yeah, yeah. Okay, okay. No, no. What this remote essentially was trying to emphasize the point on inaccessibility. It is very remote, far, and inaccessible. That was the. It's geographically remote. It is not mathematically remote. If I may be allowed to use that. I hope. Yeah. Yes. Yeah. No, actually, strain gauges. Yeah, strain gauges are quite rugged, so they can survive many this thing if they are insulated properly. It is not that strain gauge would be pasted and it will be left out. It will be properly insulated. And of course, there are calamities which we cannot anticipate. That is always there. But definitely, it has been applied in real time. It has been applied to Palm Bridge. Yeah, yes, that is why. So, strain gauge out of all the methods available at our disposal, strain gauge happens to be one which could be misused, but if it is done properly, it is quite rugged and it is quite maintenance free in that sense. Yeah, yeah. And Anil, I I hope I've answered your question about remote, what this remote meant against that. Yeah, okay, okay. All right. Okay, so which of the following statements are true related to a free surface, which we already saw? Stress vector needs to be zero on a free surface. Stress tensor needs to be zero. Stress vector, the stress vector direction on the free surface can at best be tangential to the surface. The stress tensor may or may not be zero on a free surface, and the stress vector may or may not be zero at a free surface. So actually we discussed this in quite some detail. So I suppose the answer is clear. So on a free surface, free meaning traction free is what we can take. Stress vector need to be zero. Yes. Stress tensor need not be zero, as we saw that some components might not get captured in the stress vector. The stress vector direction on a free surface can at best be tangential. We saw one example where we applied some load, let us say, and we took a point that is sufficiently away. And if we were to see this point, for that surface, with this being the coordinate system, our n is that. Sigma is, let us say I applied sigma only. So my stress tensor would be 0 sigma, and traction happens to be 0 for this particular plane, which denotes that surface. And what is the difference how stress vector behaves against a tensor is, for a particular point, a stress tensor is constant. Only it could be having different representations in different bases, different coordinate systems that we take. For example, if we were to rotate our coordinate system by 30°, our stress tensor will have some other components, but essentially it still means the same. The invariants are same. So for that point, the stress tensor is fixed once your loading is fixed. Whereas stress vector changes from plane to plane, even at that point, which all of those stress tensors are, all of those stress vectors are captured by this animal called the stress tensor. So at a point, once your stress tensor is fixed, given a normal, you will get stress vectors. So if you were to take a normal like that, which is not representative of that surface, your traction, you would see that it will be 1 0 for n equal to 1 0, sorry 0 1, which is along the y axis. You'll be able to see that your traction would be having a non-zero component. So it can at best only be tangential. It cannot be any other way. So the stress tensor may or may not be zero. Yes, we just saw that for a free surface, stress tensor need not be zero. May or may not be zero on a free surface. The stress vector may or may not be zero on a free surface by definition. Yeah, just a moment. I'll come to that question. Stress vector may or may not be zero is the literal negation of the first option. So since we have concluded the first be correct, this last one cannot hold. Organizational session question. We could find Google Sheet with information about session and about additional information. Where could we find a Google Sheet with the information about session? If you go to the Swayam portal, in our course page for experimental stress analysis, where you see week 1, week 2, on the left side bottom, it will be listed as live sessions, live session recording something. So if you click on that, that will take you to a Google Sheet where this session which we are conducting, which I'm recording, the YouTube video link for this session, as well as the PDF on which I'm writing, both will be available in that sheet. So you can access it from there, Mr. Rafael. Okay. So yeah, Found it. All right. So some experimental techniques are given below. For the following situations, identify the experimental techniques which are most suitable. For example, yeah, here it is clearly written that just enter the alphabet corresponding to the answer. Since this is computerized checking, so you will have to comply with this requirement. And if it is not clear, as I said, you please get it clarified in the forum before you answer. Okay, a technique which can be employed for real-time monitoring of a bridge. In fact, yeah, we even discussed this. Case in point being the Pamban Bridge. So strain gauges were conveniently applied there and the study took place. To identify the critical zones with high stresses and to determine the principal stress directions on a component which can later be analyzed using strain gauges. Yeah, so essentially to find out the principal stress directions, we require brittle coating. If we were just to have the identifying critical zones with high stresses, then we saw that because of Poisson's effect, stress concentration points can also be found using caustics. So the body at that point essentially behaves like a divergent or convergent lens, which will show some kind of patterns. But since the question also demands that our principal stress directions need to be found, naturally brittle coating is the way to go. To reveal the stresses produced due to assembly of a diesel engine flywheel. One thing we must keep in mind is that for very high precision, the cost also of the experimental technique goes high. Yeah. So the cost also goes high. So unnecessary precision is always to be avoided. That is, unless your, for example, if your, let us say that your rigid body motions are uh, of some order x, and if you want to measure strains that is orders of magnitude almost equal to this, then naturally you need to go for some high precision where you can segregate rigid body motion from your strains. Whereas if it is only a minuscule percentage of this, then unnecessarily going for high tech equipments is not required, in which case we can simplify our analysis. So that should always be kept in mind because these are very cost intensive and demanding experiments. So to reveal the stresses produced due to assembly of a diesel engine flywheel, we can easily go with photoelasticity because the setup for this is quite easy and it is sensitive as well as it is easy, doesn't require any vibration isolation, and post processing is almost nil. Whatever you get, you can easily post process the data from that. So essentially, photoelasticity is very much suitable for this application. And of course, we need to sometimes burn our fingers, apply some other method, find out that it has drawbacks. So the idea is that it's not to have a mental block that only this method can be applied. Many methods can be applied for the same application depending on the availability of resources and the precision that is required and the limitations that has to offer, the range of stresses or strains or displacement that we are trying to measure. All these need to be kept in mind and intelligent approximations need to be made. Okay, for determining the material properties of MEMS application. So natural, sorry, speckle, yeah, yeah. So essentially, because we are trying to characterize material properties at that this thing precision, naturally we need to go for very high precise measurements. So holography could help out with that. So, yeah, Yes, yes. Yeah, yeah. Okay, okay. Yeah. Actually, there is some work going on photoplasticity also. There are some papers which are being published in photoplasticity also. And as for the planar limitation that you said, that planar limitation only exists for your transmission photoelasticity. Whereas if the variant of photoelasticity which has contourable plastics, so if you were to apply a photoelastic coating on the diesel engine flywheel, and if you were to analyze it with a reflection polariscope, you can get over that limitation. Okay. You can apply, see, essentially speaking, in order to study this, you could also apply brittle coatings, then find out how they crack, and based on that, you can apply strain gauges. But the idea is to, if we have to find out a whole field technique which is easy and doesn't require much of a setup or cost, but is still able to deliver, so definitely it's a win-win. That is the only idea behind this. Okay. Yeah. Yeah. Above that, yeah. And also, if you see, some are very safety sensitive equipments. So, in case of a diesel engine flywheel, if you see, if we whether plastic zone is to be avoided or whether yielding is allowed is another subjective question that needs to be kept in mind. If your stress range, its operational stress range itself is within the elastic limit, nothing is stopping you from applying a technique that is only valid for that particular range. Whereas if we were to go for special applications where yielding has to be allowed, then naturally we need to look for other alternatives. So that could also be one of the ways to look at this. Because if we look for brake applications, let us say, and if we are trying to introduce fracture mechanics there, that given a crack, what will be the stress intensity factor if we start studying that? The very premise of the topic is that it is a safety sensitive equipment. In such cases, if there is a crack present, they will not be analyzing how to do remedial diagnostics for that crack. They will simply discard the component because it requires high safety. In such cases, fracture mechanics might not find applications there. Whereas if you have huge components that are very cost intensive, and if there are some manufacturing defects which need to be addressed, then naturally fracture mechanics can provide remedies for that by some patching or other diagnostics remedies with which at least we can make use of the component under specific stress ranges. So it also depends on what is the operational range of stress and what is the information that we are trying to study. I hope that is clear. Yeah. Anil, I hope yeah. Okay. Actually, I have run out of questions because 2 hours is quite a long time to be solving assignments. But if you have any other questions, I'll try to answer that because I anyway have to continue the session till 8 o'clock. So if there are any other questions in general, you please feel free to ask. Thanks, Mr. Rafael. Thank you for your feedback. Okay. So if there are any other questions in general, please feel free to ask. I'll try to elaborate on that. Or else I will try to explain a little bit about photoelasticity, which happens to be the topic for next week. Yeah. Oh, the first question that you asked. Okay, it was 1 minute. Light travels faster in ice than in calcite crystal. You are asking for the reason for this, or okay, as to why this is, or whether this is true or not. Actually, refractive index, if we see it scales down, it only gives you a measure of how much light speed is in every material as compared to vacuum. So, if you were to compare the refractive index of ice and calcite crystal, I suppose that will give you an answer. Okay. For calcite crystal, it is okay. Okay, I don't know what that minus means actually. I'll take note of this. If I get anything, then I'll perhaps get back to you. Okay, yeah. But essentially, which one travels faster can be analyzed using by just looking at the refractive index, because it is the ratio of the velocity in that medium as up against vacuum. Okay. Any other questions? Maybe from, if there are any questions from strength of material or theory of elasticity, which forms the basis for this. Okay. I have one question about problems. I'm okay with strength of material application, but I'm not good in the theory of elasticity. So, since we refer to clamped cylinder, where can we find the solution problem in feasible level? Clamped cylinder, uh, that is with a point load at the center. Okay, so actually it's not a clamped cylinder, it's a clamped plate with a point load at the center. So if this is the clamped plate and you had a point load that is coming out of plane or going into the plane of the paper. Yeah. So this you can find in any course on plates and shells. So on any course on plates and shells, if you refer to any book, maybe by I can just tell you the book name. 1 minute. This book you can just refer. So this is a book by this is the author name, and the plates and shells is theory of plates and shells is the book name where you can find the standard solution for a case of a clamped circular plate with, yeah, yes, that is the name. I'm not sure how to pronounce it, but that is the name. Ideally, how this comes about is you have a stress function. In polar coordinates, you have a general missile solution which is nothing but a stress function as a function of r, theta, then there will be some log terms and all that. So ideally, we will be based on the displacement and stress constraints that are provided, we will be ignoring the other terms. If there is an axisymmetric problem, we will be ignoring the theta dependence. So it waters down to a more tangible version that is squeezed on both sides. What about a cylinder that is squeezed on both sides? That is, if this is the cylinder you're talking about, which is this what you're asking about, Mr. Rafael? Could you unmute and ask? Maybe that will be better if it is possible for you. Because I'm not trying to, I'm not getting what you're exactly asking about a cylinder that is squeezed at both sides. And I'm not able to hear you. Okay, if you are not able to speak, then perhaps you can type it out. What I'm trying to ask is if there is a cylinder like that, if this is our cylinder, then what you mean is it is squeezed like that. Is that okay? If anybody else is getting what he's trying, point load at the, oh, like that. So this is nothing but a disk under diametral compression. If this is what you're asking, then I'll try to answer this. The fringes for which were shown in this question. This question. Okay, I'm not sure if this is from plates and shells, but essentially this comes from your theory of elasticity only. This is actually, if you see a semi-infinite plane where you have a point load applied. So you will have stress patterns that are like that. So essentially how this solution is arrived at is by adding these two and then adding one more radial tension. So the superposition of these three problems actually gives us the solution for this disk. Okay, so have you got it, Mr. Rafael? Yeah, okay. Okay, so are there any other questions? Okay, if there are not, I'll just give you a brief on what we have to discuss next week about photoelasticity. Essentially, we have a photoelastic material which shows a phenomena called stress-induced birefringence. So when it is applied with stress, it has two refractive indices. And when we have something called an optic axis, when we have normal incidence from the optic axis, what happens is both the refracted rays travel in the same line, but with a phase lag. This phase lag is what brings about different colors when we see a colorful fringe pattern in photoelasticity. And this can be directly correlated to our principal stress difference at each point in the model. So how this comes about, the mathematics that is behind this, and how to relate this, what are isoclinics and isochromatics, what causes this, how are these filters made, these are some things that we will discuss in the next session. I suppose this week, it ends the overview of experimental techniques, which discusses the basic physics that is available, that has been exploited for all these experimental techniques. Starting now, we'll be more focused on photoelasticity, that has the major thrust in this course. Variants of photoelasticity, that is reflection photoelasticity and transmission photoelasticity. The thing we spoke about, contourable plastics and reflection photoelasticity, that will come later. First, we will discuss the basics of transmission photoelasticity, which we do on polymers. The variants of photoelasticity. Then we'll cover brittle coatings and extensively cover strain gauges. So this will be the way in which the course would go. Essentially, the brief on overview of experimental methods that are available would be confined to this week alone. So starting next week, we will be delving more into rigorous mathematics and how to develop and solve some numerical problems also possibly. So if there are any other questions, please do ask. Yeah. Okay. All right. Thank you. Thank you. Actually, I'm sorry that I ran out of questions before time, because understandably 2 hours is a lot of time to be solving just one assignment, which is why I'll try to go slow and in more depth starting next time, so that we don't run into this problem. But essentially, I have tried to give you a brief of what we'll be discussing next week. It would be good if you watch the lectures thoroughly before that. And if you have any questions, please raise them in the forum. I'm also having a look at the forum so that I can collate and try to answer the questions in a more productive way. So I suppose with that, if there are no other questions, I'll call it a day. I'll end the session now, and we can meet next week, same time, 6 to 8 on Monday. Thanks. Thank you. Bye.